So I'm going to pull this cart with this spring scale across the table. Then I'm going to repeat the experiment when I pull it across the table with a 2 kilogram mass on it. And I want you to predict in which case do I need more force, with the mass on top or without, to pull with the same acceleration, and why. So when will I need more force and why? First, pulling with the mass outside, so just the mass of the cart here. This time, we'll try it with the 2 kilogram mass on it. Whoa, that was a lot bigger. Did you get it right? Did you say the one with heavier mass would take more force to pull? I suspect you did. But I also suspect the reason why might be not correct. Did you say it was because it was heavier? See, heavier implies weight, and weight is the same thing as force of gravity. Please don't be like the student who's like, hey, Mr. Collins, can you help me? Like, what's going on, man? He's like, I'm trying to figure out the weight of this object. I'm like, well, what's the force of gravity? Because I know that's 10 newtons, but I need to figure out the weight. I'm like, dude, weight and force of gravity are the same thing. And they equal the mass of the object times the gravitational field. And this is the pull of the Earth on objects. Furthermore, it is the downward pull. So you're pulling toward the center of the Earth, the downward pull of the Earth on objects. Earths pull things down. So if I were to talk about why it's heavier or why it's harder to lift, it takes more force to lift something, then heavier makes more sense because it has more weight and the Earth is pulling it down. But I wasn't talking about that. I'm talking about why when I'm pulling it across the table. The weight isn't an issue there. The weight is pulling it down. The force of gravity is pulling it down. It has nothing to do with the amount of force needed to pull it horizontally. Why would it be harder to pull it horizontally? That is something else. That has to do with mass. Mass is related to a term called inertia. We use mass and inertia interchangeably, just like you can use weight and force of gravity interchangeably. And this is the resistance of an object to accelerate. Resistance to accelerate. They are certainly related. The bigger the mass of an object, the bigger the weight will be, but there's a big difference. If you take an object, like let's say this 2 kilogram mass, and I take it where there's no gravitational field, it still has 2 kilograms of mass, it still has that inertia, that resistance to accelerate, it just no longer has Earth pulling it downward. So you still have mass even when you don't have weight, but you don't have weight if you don't have mass. They're different. And we've got to keep them straight. The unit for mass, the SI unit, is the kilogram. The SI unit for weight is the Newton. And so anytime you see a Newton talking about the weight of an object, realize that's the same thing as the force of gravity. The force of gravity should be in newtons and is a weight. And if you see a kilogram, you need to realize that's a mass. It's inertia, it's resistance to accelerate, and you can't just use them interchangeably or your whole problem will be wrong. So anytime we want to calculate a weight, we have to use a Newton. Anytime you want to have a mass, you use a kilogram. Now you're probably thinking, why normally you just measure things in pounds? Well, pounds is actually a weight. It's an English unit for weight. It's taking the mass, which is in slugs, times the acceleration in feet per second squared, and 32 feet per second squared if you're talking about the Earth's gravitational pull, and that gives you a weight in pounds, but in physics we don't use that. Okay? So please make sure you keep these separated and don't interchange them or confuse them. If you're given a mass and asked for the force of gravity, you got to multiply by the gravitational field. Excuse me, if you're given a force of gravity and asked for the mass, you have to divide by the gravitational field. Okay.
Now it is time for you guys to go ahead and try some of these. You'll see listed on the screen here 5 different numbers. And what I want you to do is to go ahead and take those and list for each one the mass and the weight. So for each one of those items there, list the mass and the weight. And probably the easiest way to organize this is just to make a chart. We'll call one side mass and the other side weight. And I'd like you to fill that out. So pause the video, like actually hit pause right now. Get out a paper and pencil and fill out that chart. Go ahead. All right. If you haven't actually done this yourself, you've not actually learned anything, I'm going to go ahead and go over this. So please go ahead and make sure you do it yourself if you have not done so. First one is 50 kilograms. 50 kilograms is a mass. So I'm going to list that as a mass. We'll label it as number 1. And I will include the unit. But what is the weight? Well, the weight is the pull of gravity, or Earth's downward pull on objects. That's force of gravity. It is equal to mg. And so we have 50 kilograms times 9.8 meters per second squared. And I got a calculator here. If you don't, you can grab one of your own. And that's 490 newtons. So the weight there would be 490 newtons. Number 2. 310 newtons, that is the weight. And if you have given a weight and we need to get the mass, you use the same formula. I'm going to substitute in for the force of gravity, the 310 newtons. And for g, the 9.8 meters per second squared. So to solve it, I have to divide both sides by 9.8. And so 310 divided by 9.8 gives me 31.6. I have 2 sig figs here, so I'm going to leave it at 2 sig figs and call that 32 kilograms. For those of you that are now screaming, why didn't I follow sig figs for the first one? Good point. I'm going to pretend that was 2 sig figs, like the 50 point in the decimal there. I hate going to 1 sig fig, so I'm going to go ahead and assume that was a 2 sig fig, and there's a decimal there, so I made 2 sig figs there. Okay, number 3, 140 kilograms. I'm going to run out of room, aren't I? We'll do it down here. 140 kilograms is obviously the mass. So we do it like we did the first one. We take our force of gravity equals mg. Therefore, the force of gravity is 140 kilograms times 9.8 meters per second squared. That is the gravitational field of the Earth. And so 140 times 9.8 is 1372, which again to 2 sig figs is 1400 newtons. So the force of gravity would be 1400 newtons. I'm going to have to erase something. So let's go ahead and put the marker back. And I'm going to do number 4, 85 grams. 85 grams is an interesting thing because that is not in proper SI units. So I have to first convert that to kilograms. There are 1,000 grams per 1 kilogram. So you would divide that by 1,000, so 0.085 kilograms would be the appropriate mass there. So for number 4, I have 0.085 kilograms. There will be room for a number 5 there down below. Okay, and then to get the force of weight or force of gravity equals mg is going to be, we'll go ahead, 0.085 kilograms times 9.8 meters per second squared. So 0.085 times 9.8, and we get 0.83 is 0.83 newtons. And so I'm going to write in here for number 4, the weight is 0.83 newtons. Awesome. The number 5, that is the last one, 53 newtons. That is the weight, 53 newtons. And so if I wanted to get the mass, force of gravity equals mg, I'm going to put in 53 newtons equals the mass times 9.8 meters per second squared. So it becomes 53 newtons divided by 9.8. And that is 5.4 kilograms. Okay. And this, being able to run through this exercise is really important. You will have to be able to distinguish mass and weight throughout this unit and the rest of your life. So anyway, that's all. I know this is a bit repetitive and it's fairly simplistic, but it's also something that a lot of people mess up on. And if you want to get the right answer, you got to keep them straight. So thank you. Have a great day.